So last time we studied geometric distribution type 1 and type 2. Right now let's consider our geometric distribution type 1, and we had probability distribution as 1 minus theta raised to x minus 1 into theta for x from 1 to infinity. Now if I want to find probability x greater than a particular value n, probability x greater than n would be nothing but probability x equal to n plus 1 plus probability x equal to n plus 2 plus probability x equal to n plus 3 and so on till infinity. Now what does this actually mean? When I say x greater than n, our x was nothing but the number of trial that was our first success. That means our first success is greater than n. That means we have at least n failures. When we say we have at least n failures, that means our success can be either n plus 1 or n plus 2 or n plus 3 or any value that is greater than n. So now I can say probability x equal to n plus 1 is nothing but 1 minus theta raised to n into theta. Then x is equals to n plus 2 will be 1 minus theta raised to n plus 1 into theta plus 1 minus theta raised to n plus 2 into theta and so on forever. Now here I can take theta as common, and just for the sake of writing I am keeping 1 minus theta as q, just so that I don't need to write 1 minus theta again and again and again. So here I can take theta as well as 1 minus theta raised to n, or I'll just write it as q. So q raised to n I have taken common, and I am left with 1 plus, here I'll have q, then I'll have q square, then q cube and so on till infinity. Now this is nothing but geometric progression. So for geometric progression or sum of geometric progression, we'll have first term as 1 and a ratio as q. So here we'll have 1 upon 1 minus q. Q is nothing but 1 minus theta. So I can say this is nothing but theta into 1 minus theta raised to n into 1 by 1 minus theta, or 1 minus theta would be nothing but theta. Theta cancel, and I am left with 1 minus theta raised to n. So probability that I will have at least n failures is nothing but 1 minus theta raised to n. Now for the next part, we'll try to find probability x greater than x plus n given x greater than n. Now what does this actually mean? Now we are saying what is the probability that we'll have at least x plus n failures when we already know that there have been n failures. So our success is greater than n, that is the given part, and we need to know when our success would be greater than x plus n. So this I can write it as probability x greater than x plus n intersection x greater than n upon probability x greater than n. Now let's consider a timeline. Now we know our value n is a positive number, positive integer, as well as x is a positive integer. So we'll have n greater than 0 as well as x plus n greater than n. Now this particular value x greater than n, I'll denote with all of these numbers. All the values that are greater than n would be denoted by x greater than n, and all the values that are greater than x plus n would be denoted by this particular line. So basically we have this line that is representing all the values that are greater than n, and we have this line that is representing all the values that are greater than x plus n. Now what is common between them, or what is the intersection that we need to find? This particular term is nothing but common to both of them. So x greater than x plus n is the intersection, or you can say that any value that is greater than x plus n will also be greater than n. So I can write the intersection between x greater than x plus n and greater than n as nothing but probability x greater than x plus n. Now, just because we just found out what is probability x greater than n, I can find what is probability x greater than x plus n. So it will be 1 minus theta raised to x plus n upon 1 minus theta raised to n. So this is nothing but 1 minus theta raised to x, or I can say it is nothing but probability x greater than x. Now what were we finding? We were finding probability that we'll have at least x plus n failures when we already know that there have been n failures. Now that is equal to probability that we'll have x more failures. Now because it is independent of n, what we call this as is memoryless property. Now what does memoryless property tell us? That what has already occurred will not affect what is going to happen. Now only 3 distributions follow memoryless property. One is definitely geometric distribution. Then we'll have negative binomial. And we have exponential. Exponential is a continuous distribution that we are going to study. So only these 3 distributions follow memoryless property. Now again, what does memoryless property actually signify? Now because this particular answer is independent of n, that means what has already occurred. We knew that there have been n failures already. Now what was the probability that we'll have x more failures? It is nothing but probability x is greater than x, or we'll have x failures. That means if I already know that I had 5 failures, it will not affect the probability that among the next 10 trials, my 10th trial will be my first success. So what has already occurred is not at all affecting what will happen. Now let's do a few sums on this property. First of all, geometric distribution sum. Now the question reads, if the probability of having a male or a female child is equal, what is the probability that a woman's 4th child is her first son? Now we can easily say our x is following geometric distribution with theta, where theta is nothing but half. Now here we are going to assume that our success is having a son. So they are saying, well, if the probability of having a male and female child is equal, so therefore theta is half, what is the probability that the woman's 4th child is her first son? Now how to recognize whether it is a geometric distribution sum or not? Simply, they have given us the probability of success, and secondly, they are asking us which trial is our first success. Now how many number of trials there can be, that has not been given. That means how many number of children that woman can have or will have is not mentioned. So it does not matter how many children that woman has. The only thing matters is that her 4th child is her first son. So therefore we need to find probability x is equals to 4. That is nothing but we'll have 1 minus theta raised to 3 into theta, and that is nothing but half cube into half, or 1 by 16. 1 by 16, that is nothing but 0.0625. Now next, let's see the next sum. The probability of having a male or a female child is equal. A woman has 2 boys and a girl. What is the probability that her next 2 children are girls? Now here they have mentioned that a woman has 2 boys and a girl. Now we know that her 3 children that are 2 boys and a girl are fixed. We don't need to find probability for that. So that has already occurred. Now what is the probability that her next 2 children are girls? Again, if we consider that having a boy is our success, so probability x is following our geometric distribution with parameter as half. Now here we can ignore her 2 boys and girl that we already know, and we have to find what is the probability that her next 2 children are girls. So we can say probability that our success, that is having a boy, is greater than 2 will be nothing but 1 minus theta raised to 2. So that is, now clearly if you see, you might say that the woman already has 2 boys and a girl, so there have already been 2 successes. This is the 3rd success, but we are ignoring those, and after that we can calculate what is our next success. The geometric distribution, because it has memoryless property, what we can have is multiple geometric distribution one after the other. Let's go to the next distribution, negative binomial distribution. Now negative binomial distribution, we write it as x is following n bin for negative binomial, and we have 2 parameters k comma theta. Now here theta is again probability of success, k is nothing but number of successes, and x is nothing but the number of trial, that is the kth success. So this is very similar to geometric distribution, or you might say there are k geometric distributions that are happening together. So again, in negative binomial we have 2 types, type 1 and type 2, similar to the geometric distribution. Now here our x is nothing but the number of trial, that is our kth success, okay, not the first success. So we already know that among our trials there have been k minus 1 successes, and the last trial or the xth trial has to be the kth success. So basically we have total x trials, out of which we have k successes, and we'll have x minus k failures. And we also know that our xth trial is our kth success. So this is the information that we know. Now let's find the probability that x will be equal to x, or the probability distribution. Now here, if I assume that my 5th trial is my 3rd success, so I can say that this position is known, that my 5th trial is definitely a success and it is the 3rd success. But what about these 4 positions? Now I can have a success, success, then failure, failure, or I can have failure, failure, success, success, or I can have failure, success, failure, success, or any form. Okay, so any of these 4 trials can be any of my 2 successes. So how would we arrange that? We would say that out of 4 trials, I will have to select 2 positions for the 2 successes, or I can say out of x minus 1 trials now, I will have to select k minus 1 successes, then I will arrange my k minus 1 successes, then I will arrange my failures, x minus k failures, and lastly, I have last trial as my success, so theta. Or you can write it as x minus 1 ck minus 1 theta raised to k 1 minus theta raised to x minus k. Now again, what are we having? We are having total, let's say, x trials, and out of that I know that the xth trial, last trial, is my kth success. So I know that the last trial has its position fixed, or last success has its position fixed. Now the other successes and other failures can have any position in these x minus 1 trials. So out of x minus 1 trials, I will select k minus 1 positions to arrange my k minus 1 successes. Then I will arrange my x minus k failures, and then the last success. Now what are the possible values of x here? Now for getting at least k successes, I would need minimum how many number of trials? Now for k successes and 0 failures, I will need at least k trials. So for k number of successes, I need at least k trials. So minimum value of x would be k, or it can be k plus 1, that means 1 failure and k successes. I can have k plus 2, or so on till infinity. I can have infinite trials to get my k successes. So x goes from k to infinity. Now let's talk about the expected value. Expected value. Now whenever we have combinations, what we do is we use logic. It is not impossible to find using combinations, but it is a lengthy process. So what we do is we skip, because that is never asked in our examination. So how do we find the expected value? So first of all, we know that negative binomial is same as k geometric distributions. So if a geometric distribution has expected value as 1 by theta, then k geometric distributions will have expected value as k by theta, or you can say each geometric distribution will have expected value as 1 by theta, and if we add all of them, we should get k by theta as our expected value of negative binomial distribution type 1. And similarly, variance, for one geometric distribution we had 1 minus theta upon theta square. So for k, we'll have k times 1 minus theta upon theta square. Now if we have type 1 negative binomial, we have similarly type 2 negative binomial. So type 2 negative binomial, we write x follows negative binomial k comma theta. For type 2, just write type 2 here. Just because we are going to use relation with x and y, so we are going to write this as another variable y. Y is following negative binomial k comma theta with type 2. Again, theta is nothing but probability of success. K is nothing but number of successes. And y is number of failures before kth success. So basically, we'll count the number of failures that we get before we can get the kth success. Now here, I can say I have y failures and I have k successes. That means total number of trials is going to be nothing but k plus y. So out of k plus y trials, I have y failures and I have k successes. I know that my last trial is going to be my kth success. That means, now if I want to find probability y is equals to y, I will have to select out of k plus y minus 1, I will have to select k minus 1 positions. Out of k plus y minus 1, I will select k minus 1 positions. Then I will arrange k minus 1 successes. I will arrange y failures, and lastly I will have a success. So I can write this as k plus y minus 1 c k minus 1 theta raised to k 1 minus theta raised to y. Now what are the possible values of y? Now for k number of successes, how many minimum number of failures can I have? I can have 0 failures, I can have all of them as successes. So y, minimum value of y is 0, or it can be 1 or 2, or we can get infinite number of failures before we get our kth success. What about the relation between y and x? We know that when y is 0, our x was k, we need k successes to get and 0 failures. So we'll have k trials and 0 failures. So I can say y is equals to x minus k. Then expected value of y would be expected value of x minus k. That is nothing but expected value of x minus, we can give individual expected values, and expected value of a constant is a constant itself. So we get this, that is nothing but k by theta minus k, or we can write it as k into 1 minus theta upon theta. Now if you see, this is nothing but k geometric distributions of type 2 will give you one negative binomial distribution of type 2. Similarly, what about the variance? Variance of y will be variance of x minus k. Variance of a constant is 0. So this will be nothing but variance of x, that is nothing but k times 1 minus theta upon theta square. Now all of these values, the probability distribution, the expected values of all the distributions are given in the table formula book that is provided to you in your examination. If you see the first section of this table formula book, we have formulas, and from page number 6 we have different distributions. Now first they have mentioned all the discrete distribution, we have binomial distribution, then we have Bernoulli's Poisson distribution, then we have negative binomial type 1, negative binomial type 2, we have geometric, where they have said geometric distribution is the same distribution as negative binomial distribution with parameter k. Okay, so what you can do is you can use probability distribution function from here. You can use the moments, that is expected value and variance from here. This PGF and MGF is something that we are going to study in chapter 5. So you can use this particular table book in your examination, so you don't need to learn all of these values. But especially there are few distributions that they might ask you to find expected value of the variance of, and usually that is a geometric distribution or a Poisson distribution of discrete. And for when we'll study continuous, I'll talk about continuous distributions also. Now let's do a question on this negative binomial distribution. If the probability that a person will believe a rumor about a scandal is in politics is 0.8, find the probability that the 9th person to hear the rumor will be the 4th person to believe it. So first of all, they have given us that the probability that a person will believe in the rumor is 0.8. So we can say theta is equal to 0.8. And they have asked us what is the probability that the 9th person to hear the rumor would be the 4th person to believe it. So we can say this is nothing but x follows negative binomial with k is nothing but 4. We need 4 successes and theta 0.8. We need to find probability that our x is equals to 9. Now simply using our formula, we can say it is going to be 8c3, then theta is nothing but 0.8 raised to 4, and 1 minus theta would be 0.2 raised to 5. So here to find the probability, we simply use our formula, and you can find 8c3 using our calculator. Now if you see in your calculator, there just above the division there is an NCR. Now NCR, all the values that are written in yellow can be used using shift, and all the values that are written in red can be used using alpha. Okay, so if you want to use this NCR, how do we use it? Just 8c3, what you will do is write 8, then shift and this division, that gives you a C, and then R is nothing but 3. So 8c3 is 56. 56 into, we'll have 0.8 raised to 4. Now for raised to, what you are going to do is, if you see, there's a button X and there's a box above it. So it is X raised to, and then you can put whatever value you need to. And if you want to, now if you see, you will have 0.8 raised to 4, and if you want to remove your cursor from that raised to value, you can press this arrow keys. So right arrow will get the cursor down. So that into 0.2 raised to 5. So that is nothing but 0.00734. Okay, good enough. We need our answer at least 3 significant numbers. That means if you are counting after decimal points, these zeros will not count. So you need at least 3 significant numbers. And if you are writing it as 734000000, these zeros will not count before decimal point. So significant numbers will be this. So at least 3 significant numbers. And if you are using fractions, let's say I have 5 divided by 2, and if you do equal to, you'll see your answer is always in fraction. How to convert this answer into decimal? What you can do is, there's just above the del and AC button, you will see a button that is named SD. Just press that and it will give you answer in decimal. And if you press it again, it will give you back into fraction. So this is how you can convert your value from fraction, answer from fraction, into a decimal number. Now this same question could have been framed so that we get the negative binomial of type 2. Now how can we frame this particular question in such a way that we get type 2 negative binomial? Now if I have asked what is the probability that 5 people will not believe the rumor before the 4th person that believes it. Okay. So that means we'll have 5 failures before fourth success. So how would we solve this particular sum? We would have said our y, you can write y, you can write x. Okay, y follows negative binomial distribution with 4, 0.8. That would be nothing but, now always if you are using type 1, you don't have to mention whether you are using type 1 or type 2. But if you are using type 2, I would suggest mention you are using type 2. Just write down type 2. So we'll have probability y is equals to, now we need 5 failures. So y is equals to 5. That would be nothing but, now for type 2, we have formula as x plus y minus 1. Our x is 4, y is 5. So we'll have x plus y minus 1. Now 8, c, we'll have not x, k. So c, k minus 1. So we'll have k minus 1 as 3, and then 0.8 raised to k, that will be 4, and then 1 minus theta, that will be 0.2 raised to y, that will be 5. So it is exactly same value. So even if you are using type 1 and type 2, you can get the same answer. So accordingly, if the question is framed differently, we'll use type 1 or type 2, even for the geometric distribution. Now next distribution is hypergeometric distribution. Now in hypergeometric distribution, what we have is, we have the trials that are not independent of each other. Now in each of these distribution, we said that probability of success for each trial was same. That means every trial were independent of each other. So even in binomial distribution, first trial might be success or failure. That does not change the probability of second being success or failure, or third being success or failure, and so on. Similarly, in geometric distribution, first being success or failure does not change the probability of second or third being success or failure, and so on for negative binomial also. But in hypergeometric, what happens is, it changes the probability of next being success or failure depending on whether the first is success or failure. Now, when we have such geometric such distributions where the trials are not independent, we need to know what kind of relations do they have. Now just an example, if out of 52 playing cards, I am selecting 2 cards without replacement. If you remember, in probability, I used a similar example when we said that the events were not independent. So basically, in hypergeometric distribution, our trials are not independent. Now if I have 52 playing cards and I am selecting 2 at random without replacement, so let's say probability of first being a 7, if I assume that if I get a 7, that is nothing but a success. So probability that my first card is 7 is nothing but 4 by 52. But probability of second card being 7 would depend on whether my first card was 7 or not. So if, first of all, whether the first card is 7 or whether it is not 7, my probability would change, because I'll have total now only 51 cards. Now if my first card was a 7, then probability of second being a 7 becomes 3 by 51, because now there are only 3 7s. And if it was not a 7, first card was not a 7, then the probability becomes 4 by 51. So we'll have such different paths. So in first event or first trial, we can have either success or failure. Now if we have success in the first trial, second trial can have again either a success or a failure. Similarly, in the first, if I have failure, I can have success or failure. And then again in the third one, I can have either success failure, or I can have success failure or success failure, success failure. So basically it becomes very difficult to define a distribution when we have so many different paths that particular probability can take. Now this probability of third being a success, when I have both successes, will be different from probability of third being a success when I have second as failure and first as success, and will also be different from this probability where second is third is success when second is success as well as first is failure. So there is no fixed distribution for hypergeometric distribution, and also in your book you will see they have only mentioned one paragraph for hypergeometric distribution, and if they ever ask you a question of hypergeometric distribution, it will look very similar to the probabilities question where we have non-independent events or dependent events. So therefore this particular hypergeometric distribution is not part of our course, or you might say is just mentioned in our book, and we are not going to find its probability distribution or expected value or variance because they will differ every single time. So next, Poisson distribution. Now Poisson distribution was derived from binomial distribution. Now problem with binomial distribution is that, let's say if I have a binomial distribution with 2000 different terms, or n is equals to 2000, and let's say whatever theta, I am not concerned what probability is right now. And if I want to find probability of x equal to, let's say 1002, now that will be nothing but 2000 c 1002 theta raised to 1002 and 1 minus theta raised to 998. Now finding this particular value 2000 c 1002 becomes very difficult. If you use your calculator and use that 2000 shift c and 1002, you will find that it says math error because it's such a large value that our calculator cannot calculate it. You can see it will be nothing but 2000 factorial by 1002 factorial 998 factorial. Now even if you remove 1002 factorial from 2000, you will still be left with 2000 into 1999 into 1998 till now these will be 998 different values and divided by 998 factorial. So it's such a large number that it will be very difficult to calculate. So when our n is really large, binomial distribution becomes very difficult to calculate. So what we do is we convert this binomial distribution into different distributions so that for large values of n, we can find the probabilities easily. Now for Poisson distribution, what we have is a large value of n and theta should be small. Now basically Poisson distribution was derived when we took n as infinite and theta as 0. So binomial distribution will be exactly equal to a Poisson distribution when n is infinite and theta is 0. So it becomes impractical. We will not have n as infinity and will not have theta as 0. So what we can say is for a large value of n and theta small, what we can have is we can have an approximate Poisson distribution that will give us approximate values that might be near to what value we were expecting. So what happens for n large and theta small? If we have x follows binomial distribution n comma theta, then x approximately follows. This particular sign is for approximately follows. Okay. Poisson distribution with, we say, a parameter lambda, where lambda is nothing but equal to n theta. Now, even though Poisson distribution was derived for the sake of finding probabilities of binomial distribution for large value of n, still Poisson distribution in itself is a distribution. Okay. So, now first of all, what is the large value of n that we require? So, n should be 100 or more, then we convert our binomial distribution into a Poisson distribution. And what value? Theta? Small. So, we usually say if n theta or n1 minus theta, if that is less than 5, then we can convert, and also n is large, that is n is more than 5, more than 100, then we can convert our binomial distribution into Poisson distribution. Now, this is not a fixed value. Okay, this is not a fixed value. Even for greater than 5, we might consider it, but what happens when we have n large as well as theta large, we convert our binomial distribution into normal distribution that we are going to study in chapter 8. So, right now, we are going to only see Poisson approximation of the binomial distribution. First, let's study the Poisson distribution. So, for Poisson distribution, I would say x follows Poisson distribution with parameter lambda. Now, lambda is nothing but rate of success per time. So, it is some rate given per some time. It might be per day, per year, it might be per month, anything. Some rate per time. So, it is rate of success. And x is nothing but number of successes. Just same as binomial distribution. Now, PDF or probability distribution function of Poisson distribution is nothing but lambda raised to x e raised to minus lambda by x factorial. Now, to find this particular probability distribution, we require the knowledge of limits that is not in our course. So, we are not going to deal into how did we get this particular distribution. So, it is lambda raised to x e raised to minus lambda upon x factorial. Now, for what values? X is equals to, now similar to binomial distribution, the minimum value of x should be 0, then it can be 1, 2, or now the maximum value for binomial distribution is nothing but n. Now, here we said that n, we are assuming it to be infinite. So, basically our x can go up till infinity. So, Poisson distribution, our values of x are nothing but from 0 to infinity, all the discrete values. Now, let's find the expected value. So, expected value, we'll have summation x into probability, x is equals to x, where x will be from 0 to infinity. That is nothing but for x is equals to 0, this term will be 0. For x is equals to 1, we'll have lambda e raised to minus lambda upon 1 factorial. 1 factorial is nothing but 1. Then plus for 2, we'll have 2 lambda square e raised to minus lambda upon 2 factorial, plus 3 lambda cube e raised to minus lambda upon 3 factorial, plus 4 lambda raised to 4 e raised to minus lambda upon 4 factorial, and so on. This will go on forever. Now, I can take lambda e raised to minus lambda common from all of these. I am left with 1 plus. Now, if I remove 2 from 2 factorial, I am left with lambda. Then here, if I remove 3 from 3 factorial, I am left with lambda square by 2 factorial. Now, here, if I remove 4 from 4 factorial, I am left with lambda cube by 3 factorial and so on. Now this is a special series. This is called as exponential series, or it is e raised to x would be nothing but 1 plus x square by 2 factorial plus x cube by 3 factorial and so on till infinity. So basically this is nothing but an exponential series that would be lambda e raised to minus lambda as it is, and this will be e raised to lambda. So e raised to minus lambda and e raised to lambda will cancel out and we will be left with lambda. So expected value of a Poisson distribution is nothing but lambda. Now it is same as if we convert our binomial distribution into Poisson distribution. So expected value is nothing but n theta, that would be lambda. Let's find the variance. For variance we'll find expected value of x square first. Now expected value of x square can be easily found out, but for this particular sum or for Poisson distribution it would be easier to find out e of x into x minus 1. So e of x into x minus 1 can be written as expected value of x square minus x. That can be written as nothing but expected value of x square minus expected value of x, or I can say expected value of x square would be e of x into x minus 1 plus e of x. So we can find expected value of x square using this particular term. So why do we need e of x into x minus 1? Because it is easier to solve this particular way. We'll just write it down. That would be nothing but summation from x is equals to 0 to infinity will be x into x minus 1 into probability x is equals to x. That is, for x is equals to 0, this term is 0. For x is equals to 1, this term is 0. So for x is equals to 2, we'll have 2 into probability will be lambda square e raised to minus lambda by 2 factorial. Then plus we'll have for x is equals to 3, 3 into 2 lambda cube e raised to minus lambda by 3 factorial plus 4 into 3 lambda raised to 4 e raised to minus lambda upon 4 factorial and so on. Now if you see here, I can remove 2 from 2 factorial. Similarly here I can remove 3 from 3 factorial, but this then becomes 2 factorial. So rather than if I had x square, if we actually find e of x square, we'll have 3 into 3. So if we remove 3 from 3 factorial, we'll have 2 factorial here. So we'll not have another term to remove 3 from. Similarly here we would have 4 square. If we remove 1 4, we would not be able to remove the other 4 and so on. Therefore, we use this term to find e of x square. It's not impossible to find e of x square. We'll have to add and subtract basically a particular term. But this way it becomes much simpler. Now, here I can take lambda square e raised to minus lambda as constant, as common, and I'll be left with 1 plus this will be nothing but lambda. Then here 4 and 3 is removed. I'm left with lambda square by 2 factorial. So next would be lambda cube by 3 factorial and so on. This is again exponential function or exponential expansion. So we get lambda square e raised to minus lambda e raised to lambda, that is nothing but lambda square. So we can find expected value of x square is nothing but lambda square minus plus lambda. So we'll have lambda square plus lambda. And what would be our variance? Variance would be expected value of x square minus expected value of x the whole square. That is lambda square plus lambda minus, we'll have lambda square, that is nothing but lambda. So for a Poisson distribution, the variance of a Poisson distribution is equal to its expected value. Now for binomial distribution, that was not the case. For binomial distribution, expected value was n theta and variance was n into theta into 1 minus theta. So even if I take theta as half, you will find n theta will be half of n, and here I'll have 1/4 of n. So in binomial distribution, the probability, so the expected value is not the same as the variance. Okay. So in Poisson distribution, we said expected value is same as variance. Now why is that different? So why do we convert our binomial distribution into Poisson distribution? Now for the sake, because if n is large and theta is small, now we said n is going to be infinite and theta will be almost equal to 0, then binomial distribution is perfectly same as a Poisson distribution. Now if theta is really very small, almost equal to 0, so I can say 1 minus theta is nothing but 1. If 1 minus theta is 1, so this n theta becomes equal to our expected value. So because Poisson distribution is nothing but a infinite n and theta very small, therefore variance and expected value of Poisson distribution is same. And this is the main reason we cannot convert a binomial distribution with large theta into Poisson distribution. So first of all, whenever we convert a binomial distribution, n should be greater than 100 and theta, or you can say n into theta or n into 1 minus theta, should be less than 5. Now when will we use n into 1 minus theta less than 5? Let's say theta is 0.99. So if theta is 0.99, it's a very large value. Probability of success is very large. But you can say probability of failure is very small. It will be 0.01. So probability of success can be converted into probability of failure. So instead of finding x being our successes, we can find x as being our failure, and we can convert our failures into Poisson distribution. We'll see that in some questions afterwards. Let's solve a few questions. If the rate at which goals are scored in a game of football is on average 3 every match, calculate the probability that more than 5 goals are scored in a match. Now here they have mentioned the rate at which we can score goals in a match. So our lambda is equals to 3 per match. So they have mentioned, so we can say x is nothing but following Poisson distribution with lambda, or you can just write 3. X follows Poisson distribution 3, and we have to find out what is the probability that more than 5 goals are scored in a match. So probability x is greater than 5. More than 5 goals are scored in a match. So more than 5 goals will be nothing but probability x is equals to 6 plus probability x is equals to 7 plus probability x is equals to 8, and so on till infinity. Or I can just say this is nothing but 1 minus probability x less than equal to 5. That can be written as 1 minus probability x is equals to 0 plus probability x is equals to 1 plus probability x is equals to 2 till this will go on till probability x is equals to 5. So if we find probability from 0 to 5, we can easily find probability either less than equal to 5, or then we can say probability greater than 5. Now simply probability x is equals to 0 is going to be lambda raised to 0 into e raised to minus lambda upon 0 factorial. Lambda raised to 0 is also 1 and 0 factorial is also 1. So we get e raised to minus lambda. Then probability x is equals to 1 is nothing but lambda raised to 1 e raised to minus lambda by 1 factorial, or I can say this is nothing but lambda by 1 into probability x is equals to 0. Similarly, probability x is equals to 2 can be written as lambda square e raised to minus lambda by 2 factorial, or just 2. That can be written as lambda by 2 into probability x is equals to 1. Similarly, probability x is equals to 3 can be written as lambda cube e raised to minus lambda by 3 factorial, that is nothing but 3 into 2, or I can write this as lambda by 3 probability x is equals to 2, and so on. Similarly, I'll get probability x is equals to 4 as lambda raised to 4 e raised to minus lambda by 4 factorial, that will be nothing but lambda by 4 probability x is equals to 3, and so on. So we can use the previous probabilities to find the next probability. So whenever we have such probabilities where we have to find multiple probabilities, consecutive probabilities, so we can use this particular method to find these probabilities of Poisson distribution. Now in our calculator, we have a good method that we can use to find these probabilities very easily. Now that is nothing but m and m plus. Now, just above your AC button you will find the button m plus, and if you want to use m plus you directly press that button. If you want to use m minus, we use shift m minus. Okay, so what does that m plus and m minus do? It just adds or subtracts a particular value from m. Okay, m is nothing but the value given above that in alpha. Okay, we'll see that. Now first of all, we can easily find this e raised to minus lambda. Okay, this probability x is equals to 0, e raised to minus lambda, lambda is 3 here, so we get shift e raised to, now you will find e raised to above ln button. Okay, so shift e raised to, and then we'll have minus 3. Shift a raised to minus 3 equal to gives me 0.049787. So either you can write that value here, all of these values, and then add them up, or what you can do is just press m plus. If you press m plus, it says answer m plus. If it has added this particular answer to m, okay, and as there was no value stored before in m, it was nothing but 0. So this is the first value that has been added. And if you see above, there's a small m written in the above line of your calculator. That shows that now a value has been stored in m. Now next value, we need lambda into 1 into probability x is equals to 0. So what we can say is just multiply this into 3. Okay, so answer is multiplied by 3 equal to gives me 0.149361, and I will add this value to m using m plus. Again it says answer m plus. So answer has been added to m plus. Now for x is equals to 2, I'll have to multiply by lambda and divide by 2. So into 3 divided by 2 will give me the answer, and then again m plus. Now for this I'll have 3 by 3. So it is same as probability x is equals to 2. So all I can do is I can press m plus again. If you press m plus more than one times, it will add the same number again and again. So be careful while using this m plus. So we can use m plus and we'll get this particular value added to that m. Now for 4, I'll multiply by 3, divide by 4, I get this value again m plus, then into 3 divide by 5 and I get fifth value and again m plus. Okay, now when we have added all the 5 values, how do we use this value m? So just press AC, it has cleared everything, but if you see there is still an m value above your line. So that shows that m value has been stored. So to use it, just press alpha and that m plus button again and it will show you an m. If you press equal to, it will show you the value. So it is 0.916082. So this probability is nothing but 1 minus 0.916082. All I have to do is 1 minus answer and that gives me 0.083917. So maximum expected answer is 3 significant numbers. I would suggest give at least 4 significant numbers. So you'll have 0.08391 or 8392. Okay. And while calculation, at least use 6 decimal points or more. Okay. So here we have this value. Now if you want to clear this m value, all you have to do is press shift and 9. If you see above 9, it is written CLR. It says clear. So shift 9 will ask you to clear either the setup, memory or all. We are not going to use any kind of setup. So either you can remove all or you can just remove memory. So all is 3, memory is 2. And then it will ask you to reset. Press equal to, then another equal to, and it will reset everything. Now you will find no value m. Now we can also store values in this A, B, C, D, E, F, X, Y and M. That is written in red. Now to store that value, I will talk about them as we need it. But if you clear your memory, it will clear all those values together. Okay. So make sure that none other values are to be used again. So only then use that m again. Now if the last value was already stored in m and then I use m plus and stuff, it will add those values to this particular value. So don't do that. Always make sure whether your m is cleared or not just by looking at the above line of your calculator. Now another way to find the value of this same sum is by your formula table book. Now in your formula table book, on page number 180, no, not 180, it starts from page number 175. From page number 175, you will find probabilities for Poisson distribution. Now for probabilities for Poisson distribution, if you see, they have given us the function tabulated is probability x less than equal to x. So they have given us values of probability x less than equal to x. If you want less than equal to, you can directly use this table. If let's say we needed to find probability x less than 5, this will be same as probability x less than equal to 4 because this is a discrete value. So if you need probability x less than 5, you can use probability x less than equal to 4. Okay. So to find these values, how do we use it? If you see, the parameter that we have used here is lambda. In this table book, they have used mu as their parameter. So therefore, just see the mu on the left hand side and find 3. 3 is on the other side or other page. Okay. So mu3, find mu3, that will be the third line, and we need probability less than equal to 5. If you see probability less than equal to 5, you are going to see 0.91608. So you can use this to find Poisson distribution probabilities also. Let's move on to the next sum. If each of the 55 million people in the UK independently has the probability 1 into 10 raised to minus 8 of being killed by a falling meteorite in a given year, calculate the probability of exactly 2 such deaths occurring in a given year. So they have given us theta, probability of dying 1 into 10 raised to minus 8, and they have given us n, that is the total number of people, that is nothing but 55 million. And we have to find what is the probability that exactly 2 people are going to die. Okay, so this is if we assume dying is success. So this is nothing but binomial distribution. So we have x follows binomial distribution with 55 million comma 1 into 10 raised to minus 8 as its probability of dying. So now because n is really large and theta is very small, we can convert this into Poisson distribution. So how do we write it? We'll say lambda is equals to n theta, that will be nothing but 55 into 10 raised to minus 8 or 0.55. 55 million into 10 raised to minus 8 will be 0.55, and then we can say x approximately follows Poisson distribution with lambda, or you can just write here 0.55, and then write we are using Poisson approximation. So this is nothing but we are using Poisson approximation to binomial distribution. You don't have to write the full term, just write Poisson approximation. Or you can even skip that. This portion is understood that you are using Poisson approximation. Now we have to find probability that x is equals to 2. Exactly 2 people die. So exactly 2 people die would be how much? It will be lambda raised to x e raised to minus lambda by x factorial, or you can say 0.55 raised to 2 e raised to minus 0.55 by 2 factorial. Use your calculator, find that value. It is 0.08726365 and so on. Again, you only need 4 significant numbers for the final answer. You don't need the whole answer. So you can write it as 0.08726. Now, simply if you see, the probability of any person dying is really low, that is 10 raised to minus 6 or 10 raised to minus 8, and still there is more than 8.5% chances, or nearly you can say 9% chance that 2 people will die in a year. And if you want to find that, let's say there at least 1 person dies with due to the meteor following, it will be probability x greater than or equal to 1. Probability x greater than or equal to 1 can be written as 1 minus probability x equals to 0. Only 0 is left out. So for that, it is going to be 1 minus e raised to minus lambda. That is going to be nothing but 0.423050. Okay. Now, what does this actually signify? Even if each person dying has a very low probability, 10 raised to minus 8, still there is a 42% chance that at least 1 person is going to die due to meteorite. Why? Because there are 55 million people. Each are having such a low probability, still there's a big chance that somebody is going to die.